Last time we were talking about the location of the equilibrium points. This is where they are for a mu of 0.1, which is actually really large. I think in the solar system, the Pluto-Charon system might be the closest to 0.1. The next largest that's significant is actually the Earth-Moon system at close to 0.01. It's like 0.012. And that's actually really large. So there's some interesting phenomena that occur in the Earth-Moon system just because of the large mass ratio. It's kind of a challenge for cislunar space. Another thing is that the moon's eccentricity isn't negligible. I think it's about 0.05, but because it is not negligible, so that means the distance between the Earth and the moon oscillates on a time scale of a month. This can have interesting resonance effects for trajectories that are in the Earth-Moon system. There's a whole bunch of interesting issues related to that. From that workshop I went to last week, one of the speakers was Aaron Rosengren, and he talked about kind of his plans for the next several years to analyze the cislunar system. The video of his talk got posted on the CELMEC YouTube website. There's a lot of interesting things that can happen, and he makes the case that people who design missions are going to need to take these into account, because either they could be putting their spacecraft on an orbit that'll always be stable and kind of always be part of the space traffic system and that we have to avoid it, or they might be accidentally using orbits that are unstable and will degrade in a few years because they didn't really consider the effects in the Earth-Moon system. So there's a lot of issues that are going to come up as we kind of go beyond geo. It's this realm of space called XGeo. But before we look at those sort of larger scale things about orbits in the three-body system, we're going to focus on just what the motion looks like around the two Lagrange points that are closest to the secondary body. So L1 and L2. And they have very similar dynamics. You can analyze them pretty similarly. That's what we're going to try to do today, and we'll see where we get. I'm considering the situation of case 3, a schematic of what things look like in the rotating frame for what we call the case 3 in energy. That means the energy, it's less than the energy of L3, but it's greater than the energy of L2. And the energy of L2 is always greater than the energy of L1. So we've got L1 here, we've got L2 here. And when we're at this sort of range of energy, two necks have opened up. We'll be kind of looking at what's happening in a region around L1 like that, or what's happening in a region around L2. So to do that, we will use some standard approaches in the analysis of equations of motion when you're near equilibrium points. So we're going to look at the motion near the equilibrium points, L1 and L2. And I said last time, all of these points are sometimes called Lagrange points. Another name maybe I didn't mention, maybe you've seen, is libration points, points that are all on that line. So if you have a spacecraft on that line with the two other masses, that's 3 masses in a row, which celestially is called syzygy. I don't know if you've heard that term, but that's kind of a neat one. Syzygy, because it's got a bunch of Y's. The Y's are all in a row. So syzygy is just 3 celestial masses in a line. They're called libration points, I think, due to the fact that there is some kind of oscillatory motion that happens. When you have oscillatory motion, that can be called libration, a librating orbit. That's not the only type of behavior that the motion near L1 and L2 have. They are notoriously unstable. And so for the first couple of centuries, they were kind of ignored in the community that studied the three-body problem. But we don't ignore them anymore. So if you've taken any course on analyzing a system and analyzing an equilibrium, a motion near an equilibrium point, there are certain things that you do. You linearize the equations of motion near that point. So I'm going to do just a little review of just generally what you do to linearize the dynamics, first near any trajectory, and then specialize to the case of an equilibrium point because it simplifies things. And then we'll analyze specifically the situation for L1 and L2 of the three-body system. So this is linearized dynamics near, I'll say, a reference trajectory. And having a sketch is probably useful here. I'll be using this sort of mathematical notation. X dot equals f of x is the full nonlinear system. And notice it doesn't depend on time, so that's good. If it depended on time, this would be a little harder to analyze. We're given, let's say, a reference trajectory. So this is actually useful for analyzing spacecraft trajectory as well. So when I say we're given a reference trajectory, that means we're given, I'll call it x bar of t, some kind of trajectory. So things are moving in time. And we want to look at nearby trajectories and see what they do. This will tell us something about the character of maybe this reference trajectory. Maybe it's a stable trajectory and things kind of move towards it. Maybe it's unstable, things move away. Maybe things just sort of oscillate around it. We want to know, to look at nearby trajectories. And by nearby, we mean mathematically in some kind of neighborhood. We'll say that there is a trajectory, and I'll just call this one x, and it'll change in time. And it will be the reference trajectory plus some displacement. I'll write that displacement in this case blue. Maybe I'll make this one nice red. So we have another nearby trajectory. We'll call that x at t. And we want to know the displacement between the two. And really, that's all we care about is how this displacement grows. So let's say here's our displacement vector. X of t is, like we wrote, it's x bar plus y. Say this is at some initial time. That's what the displacement vector looks like. At some later time, maybe the displacement vector is growing. It could be also changing direction. So maybe at some later time, pointing in a different direction. But we want to know how the displacement vector grows. So just to clarify what the terminology is, yt is a displacement from the reference trajectory. Some people call it a perturbation, but I reserve the term perturbation for other things. I think it's fine to call it a displacement.
Yes, I have a question. For the reference trajectory, are there any restrictions or best practices for picking that? Like, could you pick something that's impossible, or how do you decide what that is?
So the reference trajectory has to be a solution of the ODEs. This thing solves x dot equals f of x. So it does have to be a solution. You can't just pick any path. This has to be a solution of the ODEs.
Okay, thank you.
That's a good question. Yeah, you can't just pick, like, let's say instead of being on a Keplerian orbit, you say, I want to be on this sort of crazy thing. That would be a separate problem. You'd probably have to do a bunch of control to stay on something that's not a Keplerian orbit. But yeah, so the reference trajectory is already a solution. So we're looking at what solutions do. So the displacement from the reference trajectory, we'll say it's small. What do we mean by small? We're going to expand into certain orders in the size of the displacement. So maybe I'll write the magnitude. It is small. The magic comes in when you plug this into the ODE up here. We get x dot, which is f of x. But now I'll say, well, x is x bar plus y. The right-hand side is a function of x bar plus y. And now we'll do a Taylor series expansion about x bar. So this is a Taylor series expansion about the x bar trajectory. I guess to be careful here, let me include that these things both depend on time. And when you do a Taylor series expansion, the first term will be f of x bar. And then the next term will be this df is the Jacobian of f evaluated along the reference trajectory. When we take the Jacobian of f, this will give us an n by n matrix. And then we multiply this by y, which is a function of time as well. And then we could continue out this Taylor series if we wanted to. but we're just going to look at leading order. So I'll put a symbol, this capital O, magnitude of y squared. That just reminds us we're ignoring things that are second order and higher in the displacement. Now that was expanding the right-hand side of the ODE, but of course, x dot equals x bar dot plus y dot. So we could use that as the left-hand side over here, x bar dot plus y dot. But we said that x bar solves the ODE. That means x bar dot equals f of x bar. This thing is a function of time. So up here, these cancel out. And what are we left with? We're left with how y grows in time. So we're left with y dot equals df x bar y plus terms that are second order and higher. If we get rid of those things, just ignore things that are second order and higher, to leading order, which is fine to assume, leading order because we're saying the displacement is small. We just want to know what do sort of infinitesimally small displacement trajectories do near this reference trajectory. Then this is what we get. I think I've heard it called the variational equation. So this equation describes the leading order behavior of the displacement from the reference trajectory. And the reference trajectory in this case corresponds to y equals 0. And it's an equilibrium point of this equation. I'll call this equation equation 1. To analyze the stability of the reference trajectory, it's sufficient to analyze what happens near the origin for this equation. Instead of writing it df(xt), df is the Jacobian matrix of f. So it's an n by n matrix. It's a square matrix. We'll write that as A, and it will generally be a function of time because the reference trajectory will be changing in time. So we'll use that notation. So our ODE up there for y becomes y dot equals a t y. It's a linear time varying system. And like I said, the stability, the local phase space structure around y equals 0 gives us the stability around the reference trajectory x bar. In general, you have to use all the techniques for a linear time varying system to analyze this for a general trajectory. But what if we want to look at a special kind of trajectory? In fact, the simplest kind of trajectory. Simplest kind of trajectory would be an equilibrium point of the original system. So let's look at that. Suppose x bar, it's not a function of time. It's just x bar. It's a constant location. So an equilibrium point of the nonlinear ODE, x dot equals f of x. So this is a place where f of x goes to 0, right? And we found that for the restricted three-body problem last time. So when you have that, then the matrix A is a constant matrix because the reference trajectory is just a point. A is a constant matrix. And so the evolution of displacements is easier. Right? Now we've got y dot equals a y. Remember, this is just to leading order. So now it's a lot easier to analyze. So the dynamics around the equilibrium point are given by solutions of this ODE. We have ways to solve this. If you've taken a linear algebra course where they cover this, maybe you've seen this, that we could look at y as a function of time, and it's going to be e to the at times some initial condition, y naught. If we want to do, we could say, okay, we're done. That's the solution. But we're going to do more than that. The approach that we're going to take is to see if there are certain features of the dynamics that we can pick out. And one of the ways to do that is to do eigenanalysis of the matrix A. So instead of just doing this, which, okay, that works, we'll do something else. We'll look at the eigenvalues of A. So that means look at the determinant of A minus lambda, the identity matrix. I write the identity matrix as this sort of capital one. So this is the characteristic polynomial, and sometimes that's referred to as P sub lambda. We will look at this is the characteristic polynomial. And what do we know? We know for equilibrium points, they're unstable if any of the eigenvalues has positive real part. So if any eigenvalue has the real part of lambda is greater than 0, then the equilibrium point, y equals 0, which is the same as x bar in the full nonlinear system, is unstable. So basically, if we look at the eigenspectrum, and if we have anything that's in the right half plane, this is an unstable point. We might have a case where the eigenvalues are on the imaginary axis. If they're on the imaginary axis, then at least for a mechanical system like this, which is a Hamiltonian system, it's called neutrally stable. And you have to be careful. For most systems, if you have things on the imaginary axis, then you actually need to go to higher order terms, because it means you can't conclude stability from just the linear analysis. Fortunately for us, because of the special structure of the system here, if we do find that eigenvalues are at most on the imaginary axis, so they're not in the right half plane, they're just on the imaginary axis and the left half plane, then we've got stability. We need to take a look. So that's what we'll do. So let's go back to the system we have. We have to calculate A. Remember what A was? We'll apply this to the three-body problem. Let's apply to L1 and L2 in the circular restricted three-body problem. Now that we've got this theory. So here, x dot equals f of x, at least what we called it up above, is, I'll put it in this form. We've got x dot, y dot, this is all in the rotating frame again, vx dot, vy dot, and this x dot equals vx, y dot equals vy, vx dot equals 2 vy minus u bar x, and then this is y dot is negative 2 vx minus u bar y, where u sub x means partial u partial x, u sub y is partial u bar partial y. That's just shorthand notation. So that's the right-hand side. So this would be f of x, and then this is x dot. So we need to take the Jacobian of that right-hand side. So when we take the Jacobian, what do we get? The Jacobian, df, is 0, 0. So the first row, 0, 0. This will be 1, and then 0, and then 0, 0, 0, 1. What do we have down here? Well, it's easier to do the ones related to velocity. We'll have 2, and then down here a negative 2. And the others are a little bit trickier. What we'll have is negative u bar xx. That means 2 partial derivatives. And then this will be negative u bar xy. So the mixed partial derivatives, negative u bar xy, and then negative u bar y. So that's what we get for df evaluated for any trajectory. This simplifies when we look in particular at just L1 and L2, but maybe we'll leave it like this for now. If we had an equilibrium point, what depends on time? These terms could possibly depend on time. So let's just say we're looking at an equilibrium point. So now it's just x bar. We want to get the determinant. So we're going to have to, applying the method above, for our problem. And now here n equals 4, right? We've got a 4-dimensional phase space. The characteristic equation will be what? Determinant. Let's call this A minus lambda, and then that equals 0. So this is the 4x4 identity, the identity matrix. So this will be minus lambda 0, 1, 0, 0, minus lambda 0, 1, minus u bar xx minus u bar xy. And by the equality of mixed partial derivatives, that's why this down here is the same, minus xy minus u bar yy. Got a minus lambda 2 minus 2 minus lambda. So we have a determinant of this equals 0. I guess another way to write that is just to write the vertical bars. So that's the determinant. You can reduce this to a polynomial equation, and I'll just show you what it is. So it's lambda to the 4th minus 4 plus u bar xx plus u bar yy, lambda squared plus u bar xx u bar yy minus u bar xy squared equals 0. This looks like it's a quartic polynomial. Lambda to the 4th is the leading order term, which is what we would expect. But it's also a biquadratic, or it's a quadratic equation in lambda squared. That makes it easier to solve, or easier to find the roots. I'm not going to write the full solution of the roots, but you should be able to work it out. I'll just show you what we have here for our situation. For L1 or L2, what do we get? This is the characteristic polynomial. So maybe I'll write it as this, P lambda. P lambda is the following. P lambda equals lambda to the 4th plus 2 minus a constant parameter I'll call mu bar, and I'll say what that is, plus 1 plus mu bar minus 2 mu bar squared. And mu bar, it's related to the location of the equilibrium points. Mu bar is mu over xe, that's just the x location of the Lagrange point. Maybe I'll put it as x sub L, just to make it easier. So whether it's L1 or L2, so x sub L minus 1 plus mu raised to the 3rd power plus 1 minus mu over xl plus mu raised to the 3rd power. XL is the x location of the Lagrange point L, which is either L1 or L2. That'll be something that you would get from analyzing these second derivatives and things and just making it look compact. So it doesn't look very bad. So we've got this polynomial, and we can solve for the roots. Like I said, because this is biquadratic, it makes things easier to deal with. So let's just let alpha equal lambda squared. Then we have a quadratic equation. Alpha squared plus 2 minus mu bar alpha plus 1 plus mu bar minus 2 mu bar squared equals 0. And you can solve for alpha and find out what this is. What you'll get is that the two roots are, I'll say alpha 1, which is mu bar minus 2 plus square root 9 mu bar squared minus 8 mu bar, 1/2 times that whole thing. And then alpha 2 just has a minus sign. right? Mu bar minus 2 minus square root 9 mu bar squared minus 8 mu bar. You can work out what these are. Since this last term here, I'll highlight it there, you could figure out that this is negative. And so this quadratic equation has to have one positive and one negative root. One of these, alpha 1 or alpha 2, is positive. The way that we've written it, it turns out that alpha 1 is positive, greater than 0, and alpha 2 is less than 0. Therefore, the eigenvalues of the linearized equation near the Lagrange points are of the form plus or minus lambda, which is real, and plus or minus I nu, where nu is real. So we have a purely real pair and a purely imaginary pair, where lambda is square root of alpha 1 and nu is square root of negative alpha 2. So if we were to plot on the complex plane, what do we have here? We've got a real pair and a purely imaginary pair. And based on the theory of Hamiltonian systems, this is actually not a surprise. If you have a negative real eigenvalue, it always has to be balanced by a positive real eigenvalue. That's the same magnitude, just opposite sign. And if you have anything that's on the imaginary axis, of course, but because it's a real matrix, there has to be a negative of that. So having a real pair and imaginary pair, this is consistent with Hamiltonian theory. But it means we do have something in the right half plane over here. L1 and L2, we already know, are going to be unstable. An arbitrary small displacement near L1 or L2 will leave on the eigenvector corresponding to the eigenvalue that's positive. So L1 and L2 are unstable. They're unstable for the entire range of mu values. It gets a little bit different when we look at L4 and L5, which I'm not going to do today. Maybe we'll do it later. But they are actually unstable for certain large values of mu, around 0.03 something. So the moon is sort of close to that limit where L4 and L5, which are supposed to be, wonderful and stable, actually become unstable. But they're still stable for Earth-Moon, not in the Pluto-Charon system. So you won't find any Trojan asteroids at L4 and L5 of the Pluto-Charon system. We could also analytically work out what the stable and unstable corresponding eigenvectors are. I will just give a summary of what they are. So it's corresponding to, say, plus lambda, and I'll call this plus lambda. This is minus lambda. Here's plus I nu, here's minus I nu. Corresponding to this is an eigenvector, let's say U1, and corresponding to negative lambda is an eigenvector I'll call U2. I think this is just to be consistent with what I wrote in my book. And then corresponding to plus I nu, you can get an eigenvector, let's call it W1, and minus I nu, an eigenvector W2. Although these two are related, W2 is going to equal the complex conjugate of W1. They're both complex. This is real. U1 is real. U2 is real. W2 is not. It's actually complex. That might seem to present us a problem. What we typically then do is we would transform. You could transform from the usual rotating frame directions. And by that, I mean x, y, vx, vy. You could think of it as the rotating frame basis. You could transform to an eigenbasis, u1, u2, w1, w2. And look at solutions. Look at what the equations of motion look like in that eigenbasis. So maybe I'll first just show you what do things look like when you don't transform. So in the original basis, the equations of motion near the equilibrium point, you have to remember this is near the equilibrium point, will look like x dot, y dot, vx dot, vy dot. I'll write it this way, equals 0, 0, 1, 0, 0, 0, 0, 1. And then we've got just a constant a, 0, 0, 2, 0, minus b, minus 2, 0, x, y, vx, vy. We've already transformed, so it's with respect to the equilibrium point. So with respect to the equilibrium point, meaning here x equals 0 is at the equilibrium point. A and b are related to mu bar. A equals 2 mu bar plus 1, which is greater than 0. And b is mu bar minus 1, which is also greater than 0. That's what the linearized equations look like in the original basis. And things simplify a lot if we look in the eigenbasis. So let me say, okay, if you take that system, but now look at it in an eigenbasis, and hopefully you've seen if you transform from the original coordinates to an eigenbasis, you can diagonalize a matrix. So in the eigenbasis, maybe I shouldn't have written it this way. These are the basis vectors, but we're actually going to be using coordinates in this basis, where the first coordinate I'll call c, second coordinate eta, and then with respect to W1 and W2, I'll call these zeta1 and zeta2. So now in that basis, the eigenbasis, it actually becomes a lot simpler. C dot equals lambda c. That's the direction of growth. Eta dot is negative lambda eta. So that's the direction in which things are actually approaching the equilibrium point. And then the other two, zeta 1 dot is nu zeta 2, and zeta 2 dot is negative nu zeta 1. It's actually much easier to draw what trajectories look like in this four-dimensional eigenbasis. So what we have is, I'll write it this way, in the c direction and the eta direction, if you're exactly along the c direction, things are leaving. They're leaving the origin. This is uncoupled from everything else. These two are actually coupled, so we have to treat the zetas in some interesting way. But we would say that c direction is the unstable direction. The eta direction is the stable direction. Nearby trajectories will have a behavior that kind of looks like both. So this looks like if you've seen what a saddle is in a nonlinear dynamics course, so a phase plane. This is a saddle. And so we'll actually call this the saddle projection. And you could go from what trajectories look like in the eigenbasis back to the original basis and vice versa. Now the other directions, zeta 1, zeta 2, these are coupled in such a way that things actually look like simple harmonic motion. The motion is actually oscillating, just sort of show some oscillation. So in general, things are oscillating around. I might not have the arrows right here. Things are oscillating around. And this oscillatory projection we would call the center. So this is the saddle projection. I'm calling it a projection because really trajectories near the equilibrium point are in 4 dimensions. You're just sort of projecting. This is the center projection. So L1 and L2 are called, in the terminology of Hamiltonian systems, they're called saddle center equilibrium points. And remember, this is just infinitesimally what's happening near the equilibrium point, but this has implications for what will happen even further away. So there's a theorem that says, even though we've done a linearization here and we've ignored second order terms and higher and that displacement, this same kind of qualitative behavior holds in the full nonlinear equations. So we're not just spinning our wheels doing some kind of interesting math here. This really does have implications. What it would mean is that suppose you're able to pick an initial condition that is only in the center projection and is actually corresponds to a 0 in the saddle projection. That means that you can find trajectories that'll actually be oscillatory. Now, if they have even a little bit of a displacement away from the origin in the saddle projection, then they're going to want to move away. And that's what makes them unstable orbits. But the fact that there is a center projection, the center projection shows us that there are periodic orbits, or maybe let's just say oscillatory motion around L1 or L2. They're going to be unstable. We might say, well, yeah, they're unstable, but there's also this stable direction. Can I use that to my advantage? Yes. It means that in some sense, in the original space, let me do a sketch now of what's happening near either L1 or L2. What I'm showing is we're zooming in on a bottleneck around L1 or L2. And I think this is where I'll end. This is just sort of a schematic of what things look like in the original space. Let's just say we're limiting to a single energy. We haven't really even talked about energy in this eigenbasis stuff, but let's say, look at a single energy, a single Jacobi constant. For a given Jacobi constant in this case 3, then we've got these bottlenecks opening up around L1 or L2. Just to keep it general, I'll call this point L, where L stands for L1 or L2. And each of these trajectories in here in the center projection corresponds to one particular energy. So there is a periodic orbit that when projected onto the usual XY rotating frame coordinates, we'll have a periodic orbit. And it'll look, when we're really close to the equilibrium point, for small energies above the equilibrium point, we'll get a periodic orbit that's called a Lyapunov orbit. We have a single periodic orbit in the plane. Remember, we started from the beginning. I didn't even say it, but we were just looking at the planar circular restricted three-body problem for this analysis. You could extend this to the 3-degree of freedom problem, the spatial problem, if you want. We have a single periodic orbit, and it's often called the either horizontal Lyapunov orbit or just the Lyapunov orbit. But we also have other things. We can have trajectories that are winding onto this periodic orbit. I don't know how to draw it, but they're winding onto it. This would be something that's in the saddle projection, is starting on one of the 2 branches that's actually heading towards the origin in the saddle projection. So we have things that are winding onto, but there's also things that are winding off of. And maybe I'll do some other one that's kind of winding off of. They'll tend to have some kind of appearance like that, winding off and winding on. Technically, these are called parts of the stable manifold. We'd say it's a stable manifold of the Lyapunov orbit. And this is winding off. This would be the unstable. It's just one trajectory on the unstable manifold, the Lyapunov orbit. There's other behaviors as well. There may be trajectories that look like they're going to get near the Lyapunov orbit, but then they just sort of go on by. So they're going from one side of the Lagrange point to the other. And we have these going both ways. These things are called transit orbits. You could also have things that are non-transit. Non-transit means it sort of starts out near as if it's going to be transit, and then it just sort of bounces back, and you have this on both sides. So they come in and then they bounce back. We just call these non-transit. And really, those are the 4 categories of orbits you have. You have a periodic orbit. You have things that are asymptotic, either in forward time or in backward time to the periodic orbit. And then you have things that are transit. They go from one side to the other, or non-transit. They kind of approach this periodic orbit and then they just go away. And that's it. Those are the 4 types. So maybe we'll say more about how this fits in with the global dynamics next time. This is the picture of what things look like near the L1 and L2 points in the planar circular restricted 3-body problem. I'm done for today.
If you appreciated this video, please like and subscribe, or just wait and watch the next video in the series.